Hello everyone and welcome to this week's Premiere Pro plugin tutorial. In this one I'm going to be teaching you all about the Premiere Pro pixel types and how to convert them as well as upgrade any code to use them. So this tutorial is going to span a couple of different subjects. Firstly, we're going to be taking a look at the formats themselves that Premiere Pro uses that we need to be able to understand and code and convert from RGB. We're also going to be taking a look at how we can take our vibrancy plugin code that works for After Effects and change that so that it will now work for Premiere, which is a continuation on a previous video where we basically upgraded it to Premiere. Now we can actually write the functions to process those pixels. And we're also just going to be going over the different color spaces and how we can wrap our heads around them versus the standard RGB that most color spaces and programs use. As this is going to be an information-packed episode. Before we get started, I do want to remind you down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly in the channel, and down in the description you can check out the code for this in the GitHub link. We've been continually working on this vibrancy plugin code, and we're just going to keep upgrading it and learning more about plugins. Make sure you follow us there on GitHub for coding updates, and in the description follow us on Instagram for other live updates. If you're not already a member of the Discord server, you can come and join and get help with scripting, extensions, plugins, submit tutorial ideas, hang out with a lot of our members and very knowledgeable people who are constantly helping, asking questions, and sharing cool stuff. And if you'd like to help support us on YouTube and get cool perks, you can become a member, supporter, premium supporter, or VIP. Link for that is in the description. So in this tutorial here in the eye icon, we last upgraded this vibrancy plugin, at least the base code of it, so that it would run in Premiere. We didn't program the actual pixel modification functions, but we did give this outlining code here in the render function, which checks the destination pixel format that we're going to be using. And if you weren't already aware, these are the formats that we're going to be going over today. There's basically two different formats that we're talking about, BGRA and VUYA. BGRA is quite simple, and as you can imagine, this is quite similar to RGBA, red, green, blue, alpha. In this case, the channels are just switched from RGBA to BGRA. The other color format is VUYA, which you may know as a variety of different formats, but this is basically stands for blue tint, red tint, luminosity, and alpha. These are the two formats we're going to be dealing with. Converting and using BGRA is obviously a bit easier because we just have swapped channels that we need to deal with, and VUYA is what I like to call it, is a little bit more complicated because there's conversion and a different color space we have to wrap our heads around. So let's try and wrap our head around it. A couple of good tools is this Wikipedia page for the YUV color space, as well as colorizer.org has an RGB and down here a YPBPR or YUV color picker. Now this is of course a good way to get a feel for how affecting the different channels affects these colors. So if I mess around with the RGB, you can see by increasing the red and decreasing everything else, I get pure red, and I can adjust or add colors from these other channels and understand how adding blue and green or red and green together makes different colors. That's probably something you're already familiar with from just using computers in general or any artistic programs with the color picker. But using YUV, we need to start understanding things a little bit differently. The Y value is the luminance. This is how bright our color is. So if the luminance is set to 0, that's the darkest it can be, and it can go all the way up to 1. This of course can depend on what kind of specific pixel you're using, but in general it's 0 to 1. If you had like a YUV that was required to be 0 to 255, you could also do that. Then we have PR, which is basically the red tint. If we add to the red tint, we start to get a pinkish red color. If we subtract from the red tint and go into the negative, which this color space allows, we get the opposite, which is a cyan or blue color. So we have pink and cyan, which, if you're familiar, is basically a magenta and cyan, which, if you use a lot of print formatting, is quite familiar. Then we have the PB channel, or the blue tint. As we increase the blue tint, we get more blue color. And of course, right now we have really bright, so it's a little bit pinkish, but we can also reduce the PR to make it more blue. And then if we reduce the PB channel, it starts to be more greenish yellow, depending on what your other values are. So as you can see, the YUV or YPBPR color space is not as intuitive as RGB because we don't use it so much. But essentially all you need to know is, aside from the obvious alpha channel, there's a luminance channel, which tells you how bright the color is going to be, anywhere from black to white or bright. Then you have a red tint, which allows you to go into the positive or negative, as well as a blue tint, which allows you to go positive or negative. And the combination of all these allows us to create all the different colors inside of the color spectrum, just like we can in RGB, but with different types of values. Now, there's no necessarily easy way to just take these and do math to them. So a lot of times in plugins, we're going to be converting this to RGB, modifying the RGB value, and then converting it back to the YUV format. Now, going back to the YUV wiki page, this is how you can get a little bit more of a visual feel for how this works, as well as some useful algorithms. This right here is the best description, I think, of just understanding the general way it works. Here is V, which is basically the tint red, or the PB value, or the PR value, and then this U here is our PB, or the tint blue. As we approach 0.5, it turns more blue, and as we approach negative 0.5, it turns more greenish yellow. And for the red tint, as we approach 0.5, we reach a pinkish red, and as we go the opposite direction, a cyanish green. So that's the basics of how that works. And you can also see here, this is the Y and U and V components of an image. Here's the original image. This is just the luminance. This is the blue tint, I believe, and this would be the red tint. It might be the other way around, actually. But this is a similar function in how you have a red, green, and blue channel all meshed together to create a normal looking image. And as you just scroll down here, you can see there are a ton of different conversion algorithms, some of which are much more accurate than others. And then here's a couple of examples of the same spectrum, but with different Y values or different luma values. So with the luma value of 0, it's quite dark. And as we increase up to 1, it becomes very bright, and just the highlights. Also, I really like this kind of visualization. This is also going to be very helpful in a later in-depth tutorial where we discuss LUTs, or lookup tables, which are going to be a 3-dimensional version of this. But this essentially shows you the color gamut of HDTV and Ultra HDTV. And what this means is this is the whole spectrum of colors that can be represented on a TV. And these inner shapes, these inner triangles to be exact, these all represent even smaller sort of color spaces. So just between like RGB and YUV formats, they can have different curves or different shapes within this entire color range, and that gives you access to different things. So that's just a little touching up on how that works. This is a representation of an entire color space, and you can have shapes inside of it, which you can think of like color correction. If you crush down a lot of the colors into a more defined space, it becomes a different shape within a curve. But again, down here, some pseudocode even for converting between YUV and RGB, and I'm going to be going over how we can do that today quite easily with a couple lines of code. And let's go ahead and get started upgrading our vibrancy plugin to work with Adobe Premiere. I'm going to give one caveat to this, and that is that 2 of these formats I've never been able to come across or discover, and that specifically is VUYA 8 and RGBA 32. I've only been able to have a video in Premiere be BGRA 8 and VUYA 32, which you can think of like 32 bits per channel and 8 bits per channel. And typically the way this works is that 8-bit BGRA video is usually like some kind of AVI or old format video, and the most common is VUYA 32 float types, which are usually just any MP4 video. So here I have a video here that is an MP4, and if I hit Control-Shift-F9 on a Mac, I assume that's Command-Shift F9, and just hit play and pause real quick, you can see we're now going to get some debug information inside of Premiere. The main thing we want to look at here is the format it gives us. In this case, it's using YUV 420 MPEG-4. This is telling us that the format that this is going to require us to program in order to modify it with a plugin is a YUV format. And in this case, it's 32 bits per channel, which is the 32 float. And then here I have a very old video which is in WMV formats, and this one is BGRX, which is the same thing as saying BGRA, and this is an 8-bit color space, which is our other one that we're dealing with. So this color space here, this color space here is good. I have seen this one many times, and this one here, VUYA 32 float, is also good. These other two, I have not been able to find a video or create a video that covers these formats. If you do find this and can inform me, please do. I would love to be able to use both of these formats and figure out the minute differences between 32 and 8-bit colors. But most of the time for these, I just honestly program something temporary using the other code that I know works and hope it works. So if you know a VUYA 8-bit video or a BGRA 32 float video, please send it and let me know so I can do some testing and add an update to this sort of course of upgrading your plugin. So starting off with BGRA, this is going to be the much easier form of conversion, and I have a little guide here which just tells us how this is really going to be formatted. When we receive an in pixel, when we're running through pixel by pixel of our image, it's not going to be the red channel has the red pixels and the blue channel has the blue pixels. Because we're in BGRA, this is modified. So how does it actually happen? The input red channel is really the green channel. The green channel is really the red channel. The blue channel is really the alpha channel, and the alpha channel is really the blue channel. That's something you can easily learn and already know that. So if I have a pixel and I'm looking at a breakpoint or something, if I'm looking at the red part of the red channel, I know that's the green channel in reality. So this is something we need to know, because when we also give it the output pixel, the output red channel ends up being the green channel, the output green channel becomes the red channel, the blue channel becomes the alpha channel, and the alpha channel becomes the blue. If you were to put the output red channel as my color.red channel, it's actually going to have some weird effects, as it's going to tint your various channels totally different colors or totally different values, giving you strange results. So that's one thing to check for in the future. If you're working in this BGRA format, or even VUYA, which we'll go over in a second, is that if your image looks kind of right, but the colors are really weird or inverted, this might be why. So the nice thing about BGRA is there's not really any color space conversions required. We just need to take account those different channels. So what I'm going to do now is create our BGRA 8-bit color function. We're going to start off taking our tint function 8, and we're just going to copy and paste it. We'll call this tint function BGRA 8. That way we know we have a separate format here. And we'll go back into the render function. And we need to now have a Premiere iterate function. So I believe I can just say error is equal to suites dot iterate 8 suite 1, and that's a method, and we'll point to iterate, and we need our in data. We need our progress base, or the starting point that we're going to analyze, or 0. Our progress final will be our output dot width. Our source is going to be our input layer. In this case, that'll be a pointer to our params vibrancy underscore input, and that needs to be a u.ld. Does it just need to be? I think it's just a layer def. The next property is an area. That's going to be null to do the whole thing. Our refcon, we need to probably just copy this code here. Void pointer using our structured data here, GIP. Next we have the, I think, destination, or is that the function? Yeah, the function is next. So we'll say tint function BGRA 8, and then we want to put all this to the output. And I believe that should work just like that. Now we can go ahead and go into the function and figure out how we can make this work. And actually, this is pretty much the After Effects version of this code. I'm going to update it based on this project here. And you'll see that there's a slight difference. So in this case, instead of saying error is equal to, we're just going to say iterate 8 suite. We'll iterate using our in data from 0 to our output height, or pointer to the height. We're going to use our input, which is our vibrancy underscore input, pointer to the layer def, and then say null. We use our pointer to our data here. We need our tint function 8, and we're going to say that goes to the output. So that was just slightly different. You do need to realize the different things that you can do, like iterate suites, do differ in After Effects and Premiere, but usually you can quite easily find them close by, or check the example projects like the SDK Noise and some of the SDK Proc Amp and other test projects. So we now have this iterate suite. Let's go into our tint function, and let's just modify this so that we know it works for this. Now, firstly, we have color, which we're analyzing for important channels. We need to actually not modify this at all, because if you remember, we have a tint color that the user selects in this plugin. That is not going to come in inverted all weird like we discussed. The pixels are really going to be green and red and stuff. That only applies to our input and output pixels. Everything else in between we can kind of think of as a normal RGB color space. So when we check for is important color channel 8, I'm just going to double check what that does. Basically, it's checking if a pixel has more strength towards a certain channel, which is fine the way it's working here. We don't need to flip those around. As you can see here, we have our first check using our input P. What we're checking is if our input alpha is greater than 0. Well, in this case, what input alpha really means is our input blue. So what we need to say to make sure it's the alpha is refer to the blue. That's going to give us whatever the alpha value really is because of our pixel change, basically, our channel changes. Now down here, we're setting our output red to our color red times vibrance. That's again not correct. This needs to be our output green. Anything using our output red needs to become green. Anything using output green needs to become output red. So we're going to say our output red is equal to our color green times this vibrance value. Then we'll also say anything that refers to blue needs to be alpha, and anything that's alpha, including our in and out P, it needs to be the blue channel. And then here, where we set else red to red, green to green, blue to blue, alpha to alpha, that's totally fine the way it is because we're not making any changes to the original pixels or channels. So to recap, in order to basically make a BGRA function work for a BGRA color space, you just need to take into account that your channels are going to be flipped. The red channel is going to be in the green channel, the green channel is going to be in the red channel, the blue channel is going to be in the alpha channel, and the alpha channel is going to be in the blue channel. So you can take an input pixel and basically convert that into an RGB pixel, so it has the proper array of values. Do your math, then make sure the output refers to those same switched up channels. Now, there's also the VUYA portion of this, which is going to require us to first convert to RGB. Then again, we can do all of our math, and then we basically want to convert it back to the VUYA format. When we get an input and an output pixel in this case, it's going to be giving us basically what appears like RGB values, but all those values are going to be mapped to luma, red tint, and blue tint alongside alpha. Well, we also need to have a special iterate float function. For this, I'm going to copy it from a different set of code, and you'll be able to access that in the description. I'll go ahead and put it inside of the guide now. What this is for is essentially so that you can convert or iterate through pixels in a float format in Premiere. There's no native function or method that allows you to do this. It only works for lower bit rates, like 8 bits per channel. But what this will basically do is do the same thing that the normal iterate function does and loop through all of your pixels and apply whatever function you choose. So with this iterate float function, go ahead and actually put it above render. Make sure that doesn't give any errors. Looks good. Now we can go ahead and write our iterate float function for our VUI 32 bits color. So we'll go ahead and call our iterate float function. We need to spell it correctly. Iterate float. The first value, like a normal iterate function, is going to be our in data. Next is our progress base, or basically the Y starting point of our pixel by pixel analysis. Then we need our progress final. I'll put our output.height for that. Then we need our source. This is again going to be our vibrancy input. Next we need our void pointer to our refcon, I believe. Yes, there's no argument here for the rectangle. Then we need the name of the function itself. We haven't defined it yet, but we're just going to say tint function VUYA 32. And then lastly, our destination, which is going to be our output. Now we need to go ahead, go up to our tint BGRA function here. I'm going to copy and paste it and change the name to VUYA 32. This does not deal with 8 bits per channel pixels. These need to be 32, or you can also say float, which is the exact same thing. And then we can go ahead and learn how we can convert this and modify it to functionally work. So I have here a bit of code which we can use to sort of understand how this is working. Remember, with our BGRA colors, the red channel is really the green channel is really the red. Well, when we deal with VUYA, what appears to be the red channel that's incoming is really our tint blue channel. What appears to be our green channel will be the actual value of our luma channel, or luminance. The blue channel will contain the alpha, just like before, and the alpha channel will contain the red tint. So first value, the red channel, is going to be somewhere between -5 or -0.5 and +0.5. The green value is going to be, I believe, between 0 and 1, but I think in some cases the luminance can actually go higher. The blue channel is going to contain between 0 and 1, because again, we're dealing with float, so it's going to be in the range of 0 to 1 for most values. And then for the alpha, which is really going to be our red tint, that will be somewhere in the range of -0.5 to +0.5. So now that we have the information, we need to take that input pixel, convert it to RGB. Then you can use that now variable storing that RGB information, do whatever math you want to it, and then we can convert it back to VUYA and put it in the appropriate channels, the blue tint being in the red channel, etc. So what I have here is an example of how we can convert this pixel. We're going to first convert this pixel essentially to a VUYA 32 format. This means that we can use actual properties that match this pixel depth. We don't have to say the red channel, the green channel. We can actually say luma, blue tint, red tint, and set that equal to the appropriate channels. So because we defined these in our H file, we have type struct for our BGRA 8, VUYA 8, BGRA 32, and VUYA 32, each with the properties listed here. We can now create pixels to represent this. So I'm going to go ahead and define a PF pixel. And if I go down here, let's see if we find PF pixel VUI 32F. We're going to call this converted pixel because we're going to convert our input pixel to this actual YUVA format, and then we're going to convert that into an RGB pixel, which we can later convert back if we need to. So our converted pixel dot Luma is going to be equal to something. And then we have our other channels, the PB, PR, and the alpha. Now, if we put these side by side, let's use our guide again here. The input red is really the PB. That tells us that PB needs to equal our input red. Then we have input green is really the luma or the Y. So our luma needs to equal np dot green or pointer to the green. Our red tint is really in the alpha channel. So we can say np alpha. And our alpha channel is really contained in the blue channel. So I'll say np blue. Now we have a successfully created VUYA 32 pixel, which has appropriate luma, blue tint, red tint, and alpha values. I know this has been a long tutorial so far, and I keep saying a lot of the same stuff over and over, but that's really how you start to learn this stuff, is you have to just have repetition and really use and convert these pixel types to start understanding them and how all the color spaces can be sort of almost converted together or manipulated. So this converted pixel here now represents our YUVA 32 pixel. Let's convert that into RGB values. I'm not going to create an actual RGB pixel. I'm just going to use FP longs here to have an R value, a G value, and a B value. Now this algorithm is taken straight from that wiki page. We're taking the luma, adding this value and multiplying it by the red tint to get the R color, the R value. We're taking the luma, subtracting this and multiplying it and doing some other math to get the G value, and then doing some math to get the B value. So after we've done this math, our RGB values have been figured out. But actually, that's to decide if the color is important. That actually doesn't matter here. But this should probably be made for a 32-bit color. Or is this color only 8? Okay, that doesn't matter. I'm just checking to see if any of this needs to be updated. So remember that this was needing to be alpha. The input alpha was greater than 0. Again, our blue channel is encoded in the alpha channel, so that code is fine to stay. But now we have all these output values. This else statement is fine because, again, that just is an indication that nothing is happening, so just keep the pixel the exact same. But now we're dealing with something a little bit different, where we need to take a channel and multiply it by vibrance to create this output. So our converted pixel, we've converted into these RGB values. So we have the actual input values. Now I'm going to create a couple more temporary variables. I'm going to create PF FP long, which can store pretty much anything. I'm going to call this new R. I'm going to have new G and new B, because we need to actually convert before we go back into these values. So our new R is going to be equal to our color red times vibrance. Our new G is going to be equal to our color red. Or actually, we just need to replace our R's here. This needs to be new G and new B. And then our output blue is still going to be output blue. Remembering that blue is equal to alpha, but the output values of this need to not be RGB, they need to be VUYA. So now that I have that done, we have RGB. We need to convert these new R, new G, and new B colors back to VUYA. So here's yet another algorithm I need to add here to convert from these RGB values back into VUYA. I have the wrong variable here, but I'm going to recycle this converted pixel. I've already done some math with it, so I don't really care. I'm going to say converted pixel dot luma is equal to, instead of output pixel RGB, I don't have that. In this case, we're just going to use new R for the reds, new green, new G I mean, and new B for new blue. The luma needs to be updated to that. This needs to be new R. This needs to be converted pixel. So let's recap at what we're doing here, and actually first let's add this into our document here. convert back from RGB to VUYA, recycling our converted pixel variable. So there, now we have that. That will be updated in the guide as well. So to recap, how are we going about this VUYA process? BGRA is a bit more understandable, but how do we do this? Our input pixel, we know the channels are a little bit flipped around. So the first thing we do is create a pixel type that is fitting of the color space we're in, VUYA 32. Instead of having to deal with RG and B channels, let's deal with the real channels that exist, Luma, PB, PR, and alpha. So we're simply mapping the correct input channels to these properties in our converted pixel here. We're saying converted pixel because we're converting the input into the proper format. So our Luma becomes the input green, our blue tint becomes the input red, our red tint becomes the input alpha, and just like in the previous example, our alpha becomes the input blue. Although I didn't actually have to use these values, what I also did is created an RG and B variable to convert that VUYA format from the input into an RGB value. The reason I didn't use it is because this is a tint plugin, so I didn't actually need to use the input pixel. This is just how you would convert VUYA into RGB. But we do have an 8-bit color here, which we do use. And one problem with that as well is that's going to be 0 to 255. So I need to create a PF pixel 32, color 32. Say color 32 red is equal to our color.red divided by 255. And we're going to do this for each of the channels so we can quickly convert it. So this is just math to quickly take alpha, red. So this is just math to quickly take these this 8-bit color and turn it into a 32-bit color, which we can then instead, we know that's fine, make it like this. That way we're not dealing with the wrong values here. So to recap, we have an input pixel. We're remapping those values. We convert them into a VUYA pixel, just so we can have proper representation of the pixel if we need. Maybe you have a specific algorithm that doesn't use RGBA. Then this is how you can convert VUYA values to RGB. Again, we didn't use them because we're going to use this custom tint color coming in from the UI, not the input pixel here. We check if the channels are important. That's not important to this tutorial. If the alpha is greater than 0, because the alpha is contained in the blue channel, we are going to calculate a new R value. In the previous code, this is the output red, output green, and output B, but we're not going to give it an output red, green, and blue because this is not a red, green, and blue color situation. We're simply doing the math in the background. We're calculating what the red should be, what the green should be, and what the blue should be based on a tint amount, the vibrance, times whatever this color is that the user selects. Then finally, we're going to reuse that converted pixel, which is just a VUYA pixel. We're going to get the Luma, blue tint, red tint, and alpha values of that by using this algorithm here based on our conversion from these RGB values. And now we just need to set them. So we'll say output out P, red is equal to something, green is equal to something, and we already have the blue down here, but we need the alpha, which is going to be what channel here? We have the red channel is really the PB. So our output red is going to be our converted pixel PB. The green channel is really the Y. So we're going to take our converted Luma and set that equal to the green channel. And that makes the red tint, the PR, equal to the alpha channel. All right, I think it's time that we try and test this. I'll go to my properties, debugging, and instead of debugging this in After Effects, I'll make sure we're in Premiere. And cross your fingers, we'll build it. I probably should have checked along the way, but honestly, I had a render going in the background, and I just let it do its thing. Let's go ahead and hit the debug button and see what we can accomplish. So I'm going to load up my project here with a BGRA comp or sequence and a YUV one. Let's start with this one. Go to into productions vibrancy, and it seems to be working. This is not a good example of footage because it just is going to tint the whole thing that color. Usually use like an explosion, which is something I got to work on. That seems to be working. The color tint is taking it in perfectly fine. If you were messing up those channels, it wouldn't have appeared the color you were tinted. It would have been something different. Now let's apply it to this VUYA footage. As you can see, it's tinting it the same intensity. Let me see if I can download an explosion or use like a stock footage of an explosion. Let's go ahead and just use an Action Essentials explosion. It won't let me import it. Import an explosion. Open it in a comp, or a sequence I should say. This is actually giving us BGRA, so that's interesting. It's not actually in VUYA, but that's fine. We can still test this. Add vibrancy, and there we go. There's our proof that the BGRA is indeed working. The explosion is the prime example of this plugin, and as you can see, we can go ahead and tint it something gross looking. Adjust the gamma. Gamma needs work. The vibrance we can adjust, and yeah, that pretty much shows that it's working well. And this is working too. I just don't have, I guess, an MP4 explosion to use. I can maybe try some particles and see if that works. It's showing as YUV, which is good. Apply vibrancy. It's too strong. Well, that pretty much shows how you can deal with different pixel formats, which are mostly right now exclusive to Premiere Pro. There's a couple of steps again just to remind you of how you can get going with this. I'll have this link to this code in the description where you can learn how to convert the pixels, what the input channels really mean when you're dealing with these pixel formats, this custom iterate float function to use float bit rates inside of Premiere. Again, you also want to reference some color pickers like colorizer.org. Look into the wiki page on YUV color spaces for other conversions and just in general how the theory of all this works. And then, of course, inside of your render function, make sure you don't forget to create a function or a method for each of your different pixel depths and pixel types here. And you'll be on your way to completely converting your plugin to work for Premiere. But that's going to do it for this video. I hope you guys enjoyed. If you did, hit the thumbs up button. Down below, hit subscribe and the bell icon to be notified of new videos coming out twice weekly in the channel. And down in the description, again, you can check out the code for this in the GitHub link. Make sure you follow us there for coding updates. And in the description, follow us on Instagram for other live updates. If you're not a member of the Discord server, you can come and join and get help with scripting, extensions, plugins, expressions, submit tutorial ideas, and much more. And if you'd like to help support the YouTube channel and get cool perks, you can become a member, supporter, premium supporter, or VIP, link in the description. Thanks again for watching this in-depth tutorial, guys. I'm going to be making a lot more like this in the near future. Thanks again for watching. We'll see you next time.